Jor's colleague for a while, right?
That's right. Jor not only records all the things going on in his office, he posts them to the internet and makes them freely available. Every idea I've ever had,
yeah,
in my pensive, and it's amazing. So
it's never gonna work. Okay, so I guess now the camera is running, so I should say something. But since this is supposed to be a pre-talk, just everyone should be very aggressive to interrupt as much as you want. Like, I don't know, with whatever. So I'm Theo, and I'm I'm a category theorist first, but I masquerade as a physicist sometimes. And I was sort of thinking about something to tell you guys, and I thought I might say something about semi-simple higher categories, if that was interesting. In particular, I'd like hopefully to mention a question that if anyone's looking for a question to solve, that I think it needs to be solved. So the idea of semi-simple higher categories, well, what's the idea? So what's the motivation? The motivation is we want to do representation theory. We want to do higher dimensional, higher categorical representation theory. And one of the most basic questions you should ask when you're studying representation theory is, are the representations sort of completely reducible? Are and more generally, kind of what is the sort of linear structure, the homological structure or whatever, what is the linear structure of the category of representations? And so I'd like to at least tell you what that kind of working definition, this is really a working definition, maybe, of what I think a semi-simple higher category should be, and some versions of it. So as a warm-up, what's a semi-simple lower category? Well, semi-simple, kind of one category. Let's work over some fields, I don't care. Is, well, it should be, of course, linear. So it should be K-linear. It should be additive and Karubi complete. It really should be abelian, but in a moment I'm going to say something that will imply that it's abelian for free. So Karubi complete, let me just remind, and I'll say this more in a moment, Karubi complete is sort of a very mild version of abelian, very weak version of abelian. That just insists on very special, that sort of just insists on sort of what you might call split kernels and co-kernels. Please interrupt with questions because I didn't really think about how to present anything anyway, so you won't throw me off for this 30 minutes. But Dave's seen versions of this before, so he can interrupt too. So it should be linear, additive, and Karubi complete. And then most importantly, every object should be decomposable as a direct sum of simple objects. And I should tell you what a simple object is. A simple object is one where there's various ways you could say what simple means. And in non-semi-simple categories, different definitions are going to be different. But for semi-simple categories, they're all going to give the same answer. So I'll give the one that actually is going to work well for the generalization I'm going to give. So I'm going to say X is simple if any non-zero, okay, it should be not zero. And any non-zero map to X let's say it splits. Well, that's a very strong condition. That would be like simple and projective, but that's good enough. So what you'd really want us to say, any non-zero map is a surjection. And well, in the semi-simple world, as I said, I don't actually, well, the problem is I don't know how to say the word surjection in higher categories. So what I'll say instead is,
you can't say like an epi kind of thing, or like isn't there some Schulman version of epi that?
Yeah, so you can sort of say surjection. So a surjection is a map so that when you test it against representable sheaves, it's always injective. So an epi is a map which, when you test it against representable sheaves, is always injective. And so in higher categories, you could say that where you'd want it to be injective at all levels. So injective on morphisms of every dimension. Injective on morphisms of every dimension is not a terrible thing, but it's not a great thing, because kind of injectivity at some levels sort of feels a lot like surjectivity at other levels. And so it's a sort of a weird notion. Like, it's not, you can do it, and people do it, and in algebraic topology it can be important, but it's still a sort of, there's some conflict between injectivity at different levels. So instead of that, what I'll just say is that what I will demand something stronger, which will follow from kind of this condition. I will demand that it's a split surjection. So what is a split surjection? That's a map. That means that there exists a map going the other way, so that the composition, so that going up and back down is the identity on X. And since I have you all paying attention to me, I'm just going to continue to proselytize and that's not what I meant to do. I want to continue to proselytize a notation, which is that we should write this as Y mapping with a hook to X. I just think that that's a useful notation, and I offer the tech code to anyone who wants it. Or you can just write it yourself. Okay, so that's what a semisimple one category is. And now I can just go through and change 1 to n. And now you know the definition. Well, you don't quite know the definition. There's two things I should tell you what to do about. So there's two things I should tell you about. One is I need to tell you what this word Karubi complete means. So I owe you an n category version of that term, and I owe you an n category version of split surjection. Why do I owe you an n category version of split surjection? Well, because of this equality here. Equality is sort of never the right thing in higher categories. And as anytime you see an equality, that should sort of make you think, oh, there's some sort of user defined, like there's some sort of thing I should actually think about. Or how to say that. Okay, so let me tell you about these two things. So sorry, before, yeah, I'll say it this way. So Karubi completeness is something that's very wrapped up in split surjections. I mean, I even kind of, I think I even said Karubi completeness was that sort of certain things have kernels and co-kernels. Well, specifically kind of split maps have kernels and co-kernels. So to tell you what Karubi completeness means, I should tell you first what is a split surjection. So in an n category, a split surjection, I'll just write kind of, I'll just use my favorite notation. Let's see, X split surjects to, oh wait, Oh dear. Well, X and Y just switched, but if I don't put them in the order that I have them in my head, then I won't get the formula right. I might not get the formula right anyway, but I definitely won't get it right if I don't put it in this order. X splits surjects to Y. So to tell you this means that this is data. Is the data of, well, there should be the downward map, I'll call it F to Y. That's the thing that's supposed to be a surjection. There should be the upward map from Y to X. That's the thing that's supposed to be the splitting. And then I should witness that it is a splitting. So how do I do that? I can go up and back down. And I can compare that to the identity on Y. And the thing I'm going to request is well, I'm not going to request that they be isomorphic. That turns out to be the wrong notion. I'll say why that's the wrong notion. I'm going to request that they split surject. And the point is that this is something going on in the endomorphisms of Y, and this is an n-1 category. So it's something you've already worked out what it meant by induction. Once you know what a split surjection is, then you can work out what Karubi completeness means. So what does Karubi completeness mean? Maybe not all of you know this. I don't know. I don't actually know what any of you guys know. I mean, I know that Dave knows everything, but other than that, I don't know what any of you know. So let me remind that C is Karubi complete if every idempotent factors through a split surjection. So this tells you what an idempotent is supposed to be. An idempotent, so let me give it a name. Let's call the idempotent E. That'll be a map from an object to itself. And it should factor through a split surjection like that, in the sense that E should be G and then F. So do go down and back up. So now you know what an idempotent is. So that means that whatever an idempotent is, so an idempotent is the thing that GF is the thing is all of the axioms, all of the properties that GF satisfies if you have a split surjection. That's the definition. You sort of cover up Y, you forget about it, you just remember everything about X and its endomorphisms. But I can unpack that for you. Well, see, in the one category case, yeah, so I can unpack it for you. If you go down and up and down and up, then in the middle there, you went up and back down. Going up and back down contains Y as a sort of split surjection. Contains Y as a split surjection. I should emphasize that if you have a split surjection, say precomposing it, whatever, applying functors, it's still a split surjection. So what you find out is that kind of, as I said, so going up and around, it split surjects onto just going around. So this was E squared and this is E. And now you can start comparing, well, I can go around 3 times and I can kind of split surject out this part or that part. And it doesn't matter the order that I do. So whatever this data is, well, this is some data, let's call it M. And you find out that M, sort of this split surjection, M is associative. And it's associative in a sort of fairly complicated way, because actually M has a lot of data. It has both a downward arrow and an upward arrow, and I'm telling you a lot of axioms all at once when I say it's associative. So it's really kind of associative in the same way that a Frobenius algebra is. See, I could unpack this and I could say, well, this data was the data of a downward arrow M and an upward arrow that I'll call delta. And then the associativity here is that basically M delta is special Frobenius. So it's a quite familiar kind of, it actually unpacks to something quite familiar, and it kind of gives the kind of categorical version of either Frobenius algebra or Karubi completion.
I do have one question. In the green, you had the E equals GF. I'm a little concerned about the equality there.
That's exactly right. Okay, great. So the statement should be, so you're exactly right to be worried about that. So so the thing that I will tell you that should put your mind at ease is that so I'm going to choose it to be an isomorphism, or whatever a higher isomorphism, a higher equivalence. And then that should make you really nervous, because that might have been data. And so the statement that should make your minds at ease is that actually the theorem is that if this factorization exists, it's unique. I mean, it's unique in exactly the way things get to be unique in a higher category. That the category of all of them, I'm telling you that the category of all such factorizations is either empty or it's contractible.
Okay, thank you.
Okay. So that was what a semi-simple category was. There's a sort of, I want to talk a little bit more about, so there's another axiom. I should have given some references. So this is basically, let me say this is like, well, it's still, okay, this maybe I just told you is a definition, but I want to give a reference to this. Is sort of, I'm basically kind of, this is, all of these notions are kind of based on Douglas and Reuter's work. So David and Chris did the kind of 2 categorical version, and that's what I'm kind of, that's the sort of pedagogical structure I'm following. And then with Gallardo, we did the N category version. Okay, I wanted to mention their work. And in the paper with Gallardo, we kind of used language that came from condensed matter for all of these notions. And I like that language, but you can look at the paper to see it and you can decide. What else did I want to say? Oh, so you might add another axiom. To your request, to your definition of sort of semi-simple N category. The following request. You might add the request that all morphisms are fully dualizable. So fully adjunctable. This is a very reasonable request. I don't know any interesting examples where it fails. But I don't know whether it's morally the correct thing to include. The reason why you might add this request is because let's suppose that you have, let's suppose that X is mapping onto Y. And let's suppose that Y is sort of simple in a weak sense. So in a one category, Y is simple if and only if the endomorphisms of Y is a field, well, as a division ring. Let's just say it's the ground field, and let's assume that I'm working over an algebraically closed field. For this. So let's say that let's like study that example. Let's say that we're in an N category, and let's say that, well, you could take Y, it's an object in an N category, so you could take its endomorphisms. That's an N-1 category. Okay, I just need to give you a notation. So if you have C and an object, then there's a base loop space. Which is the endomorphisms in C of Y. That lowers the category number by 1, and you can iterate it. So this has a distinguished object in it called the identity. And so then you can just take iterated based loop spaces. So the iterated based loop space, if C is an N category, this is just a ring. In fact, a commutative ring. If C is, well, it doesn't matter that it's commutative for what I'm about to say, and it's false if it's N is 1, so I shouldn't say it if C is an N category. It's technically an EN ring. Excuse me. So let's say that we're sort of in this case where Y is simple in this weak sense. So if Y is, well, let's suppose that that it's just the ground field, but let's suppose that F has an adjoint. In fact, let's suppose that we have a lot of adjoints, that all morphisms except for top morphisms have adjoints. And that we have lots of adjoints. Well, then what you can do is you can take X, you can map it by F to Y. You can take, let's see, I think I want the, okay, I have 50% chance of getting this right. I think I want the right adjoint. Well, the right adjoint comes with a map that goes down to the identity on Y. The kind of evaluation map on F. And then I can keep going. I can take the right adjoint with 50% odds to the evaluation map, and that'll have another map down. And you keep going, and you start building. So what I'm telling you is if you have lots of dualizability, then you can start building splits rejection. And you get stuck only at the very end. And at the very end, the last step, you win if all sort of endo N-1 categories, no, all endo 1 categories. So all of the categories of top morphism, of top -1 morphisms, all of the categories of N-1 morphisms are semi-simple. Why do you win? Well, the reason you win is because at the very last step, you're in some, like you're in omega N-1 of Y. In fact, you win actually, you don't need even that. You just need, yeah, specifically you win if omega N-1 at Y is semi-simple. This is a 1 category. And because we decided that the identity object in it is simple. I mean, because of this axiom. So at the very last step, what you have is you have a map in this category, this one category, to this to the object, which is like the identity on Y at that dimension, which we just decided was simple, and we decided it was semi-simple. So somehow being locally semi-simple and having lots of adjoints implies that you're semi-simple as an N category. So should I really stop at 5 or can I go a little later? Sorry, 4. 5 in my time zone.
I think, yeah, the only danger in going a little longer is if somebody comes early to your talk to the same Zoom room, they'll think that either the talk has started or, but it's not a big deal to me. It's if you would like a break, then go for it. If not, go for it.
I want a break, but I also want to actually say one and a half more things.
Perfect.
So the summary that I just told you was that lots of dualizability plus kind of local semi-simplicity. Semi-simplicity is kind of global semi-simplicity. Oh, and kind of direct sums and Karubi completion. Oh, I should have said this. So something you guys might know is that in a one category, direct sums and Karubi completion, this goes under another name. It's called Cauchy completion.
I call both of them, I call one of them direct sum and idempotent completion. Both of those together, I call that whole thing Karubi completion.
Okay, fine. That's not the language I grew up with, but no, I refuse. I disagree with you. I think Karubi, I think that Karubi only did the idempotent completion. And Laver was the one to call it Cauchy completion.
Okay, let's have a conversation after.
Okay, fine. Idempotent completion. The reason for this Cauchy completion is something that makes sense in any enriched world. You can formulate a notion of a Cauchy completion sort of anywhere, and then it's a sort of question of unpack Cauchy completion in your world. In the linear worlds, Cauchy completion unpacks to direct sums and idempotent completion, at least for linear one category. That's the name that Laver explained. And our theorem is that these notions I told you, like this, it does get you Karubi completion in N categories. So it is the right notion of idempotent completion. I maybe should have written that, but I'm not going to because I wanted to get to one other thing. So the last thing I wanted to tell you was that sometimes you care about something stronger than just semi-simplicity. So sometimes you're studying not just a semi-simple category. What are semi-simple categories arise? In representation theory, semi-simple categories arise as the representations of compact groups. So that's how you should think about it, is that semi-simple category, that's like the representations of a compact group. But there's a very special type of compact group, which are the finite groups. And the way you should think about the representations of a finite group, well, these are the finite semi-simple categories. They're the categories with only finitely many simple objects. This lots of dualizability is sort of a finiteness condition. So that's why I don't think it's probably really part of semi-simplicity. I think it's part of finiteness. And so I wanted to give a definition. So C is finite semi-simple. This is now going to be an N category. If, well, it should have direct sums and Karubi and idempotent completion. And it should be locally finite semi-simple. So all of its Hom spaces should be finite semi-simple. So you know what that means by induction. And also it should have, well, it turns out that finitely many simple objects up to isomorphism almost never holds. So what we'd love to say is finitely many simples But that never holds. That's not the right definition. It didn't even hold, by the way, in the representations of a finite group, because of course there were infinitely many simple objects. There were just finitely many simple objects up to isomorphism. So to say finitely many simples, well, okay, so certainly finitely many simples up to iso is totally the wrong thing. It turns out as soon as you get to about 3 categories, this just never happens. It turns out that it's in conflict with Karubi completion. And you just can't have both. So the correct statement is that what's the reason for this is that already in 2 categories, it's very possible, very common for 2 non-iso simples to be related by a non-zero map. In one category, a non-zero map between simple objects is always an isomorphism. And this fails as soon as you're in 2 categories. All you know is that if the map is can extend to a split surjection in both directions. And so, but the theorem of basically of Douglas and Reuter is that that this is the theorem says that this statement, simples related by a non-zero map, this is an equivalence relation. So what you do is you sort of start with some simple, and then there's all these other simples you can get to it by non-zero maps. And then there's some other simple far away, and it has things it can get to by non-zero maps. And so the picture of this category has these different components to it. So these are the components. Sort of the pi zero of the category. And so finite semisimple, I told you finite semisimple should have been finitely many, sort of locally finite many simples. And then the last axiom is finitely many components. And now I'll stop, but I can't resist I can't stop until I tell a question that I don't know the answer to.
Theo, do you mind if I ask a question and interrupt you?
Yeah, please.
Could you go back a slide, please? So here you study a local property, which is semi-simplicity. And you say that given enough dualizability, you get a global property. Let's suppose, are there other local properties that one could possibly think of, and then you impose dualizability and get something global in the N category? Other examples you know of?
Good question. What dualizability tends to buy you, it buys you a lot. In this case, kind of, dualizability can never, for instance, directly buy you a count of the number of objects, because you just might have infinitely many different objects unrelated to each other. So it can't buy you that good global control. What dualizability tends to buy you is it tends to buy you non-zeroness. That's actually what was going on in this kind of proof that this argument that I sketched down here. What was really sort of, at the end of the day, what we were using is that these evaluation and co-evaluation maps were not zero. So it gives you lots of access to non-zero things, to knowing that something wasn't zero. And so more generally, it kind of gives you, it kind of buys you faithfulness of maps. It buys you, so yeah, so things, I don't know, things where you need something to be not zero, that's the sort of typical thing it buys you. I don't have anything better to say than that.
But it won't control the number of objects, or
no, because there just might be unrelated objects. You might have You could have taken every single person in the world and had them write down their own category, and then there'd be just infinitely many of them. Because I don't know, I kept trouble counting above like single-digit numbers. I'm certainly not going to count that. Yeah. So, oh shoot. So I wanted to say actually two things. So when you start thinking about finite semi-simple categories, a very interesting question is, what is the endomorphism ring in a finite semi-simple category look like? So if C is finite semi-simple, then kind of these loop categories I was talking about, the loops at X of C, this is an N category. Then this is a monoidal N-1 category. And if you just sort of run through what I told you, it's a finite semi-simple N-1 category, and it has lots of good dualizability. So it is a multi-fusion N-1 category. What does that mean? Multi-fusion, what is dualizability? Let me just mention what dualizability means. This means that you can take the multiplication map, usually called tensor, but I'm going to call it M for multiplication. And the dualizability is the statement that M has an adjoint among kind of A bilinear maps. That's a good way to remember the dualizability condition in a fusion category. I need to stop, I think. So let me just mention that it might not be it might not be a split surjection. And I'll just I'll pose a conjecture. So if it is a split surjection, then it's called separable. So the conjecture is that in characteristic 0, multi-fusion N categories are separable. And if somebody wants to solve that for me, it would make me really happy. Okay, I need to take a short break. When is the talk? In 5 minutes? Okay.
Yeah, 5 minutes. Okay, thanks so much. I'm going to stop the recording here, and then we'll do a new one for your talk.
Which means I don't get time for questions now, but people can, I'll stick around after.
Okay. Thank you very much.